So a fractional precipitation problem usually has a solution where they just have a mess of different ions. A lot of the times in chemistry, as we're making wastes, we like to consolidate wastes down to a single container. Usually a lot of stuff that has heavy metals, such as this sample, where we have copper, silver, and gold all smushed together in the same container in about a 0.01 molar solution of each. Now occasionally, a couple of those ions are expensive, like for example that gold, and we would want to recover that gold from the solution. So we can use a method called fractional precipitation to get that done. Now we're going to be capitalizing upon the fact that all of those ions could react with something that would make it into an insoluble compound, and in this problem we've chosen chloride ions to start that precipitation. So the first thing that we're going to want to calculate is the minimum concentration of chlorine ions that I'm going to have to add in to start the precipitation. Well, I've looked up the KSP values for each of the chloride compounds that we're going to be generating today. So we're going to start off with 3 KSP calculations. I'll speed through those right now. So I was able to plug in 0.010 molar for the concentration of both the copper, the silver, and the gold. And I plugged in X for the concentration of the chlorine. So now it's just a matter of solving for X in each case. So we should find here that X, first one, the chloride ion concentration should be 1.9 times 10 to the negative fifth. Chloride ion concentration to start precipitation of the silver should be 1.8 times 10 to the negative 8. And the chloride ion concentration for the gold should be 2.0 times 10 to the negative 11. So these would be the minimum concentrations of the chloride ion to start the precipitation of each of these 3 ions. So what we would do is we would slowly drip in the chloride ion, and eventually, once the chloride ion hit 2.0 times 10 to the negative 11th molar, we would start to see some precipitation happening, and only the gold chloride would start to precipitate. So we'd continue to increase and increase the chloride ion concentration, slowly driving out more and more the AuCl precipitate until just before the chloride ion concentration reaches the 1.8 times 10 to the negative 8 concentration. At that moment, then the silver chloride is going to start to precipitate, but not quite all of the gold chloride ion is going to precipitate out either. So we pause the titration, collect out all of the solid precipitate that we would have made at that point, knowing that it's pure AuCl, and then continue to increase the concentration, stopping just before we hit the 1.9 times 10 to the negative 5th concentration. At that moment, then the copper chloride starts to precipitate out. We could stop the titration, collect the precipitate out, and at that point we have mostly just AgCl with a tiny little bit of AuCl thrown in as well. Then the precipitation would continue, and as we go past the molarity of 1.9 times 10 to the negative 5th, then the copper chloride begins to precipitate out. Now the copper chloride is going to be contaminated with a little bit of silver and a very tiny little bit of gold. But the next question is going to be, how much? So the question is going to be phrased much like this. How much of the gold will precipitate before the silver begins to precipitate? What percent has precipitated? And then also determine how much gold remains in the solution when the silver begins to precipitate. So let's begin this lovely little calculation. So The first important point inside of the titration is when we hit that very first minimum value. So when the chloride ion hits 2.0 times 10 to the negative 11th, we know that we're going to trigger the first precipitation to occur. The AuCl starts to precipitate. Things don't get really interesting until we hit the next minimum concentration, which would be 1.8 times 10 to the negative 8th. And at that point, the AgCl starts to precipitate as well. Most of the AuCl would have come out at that point. So at the moment when the AgCl starts to precipitate, we'd like to know how much gold remains dissolved in the greater solution. So if we want to know how much Au1+ is left in the solution, we need to do a KSP calculation. Now we know the chloride ion concentration at this point, but we don't know what is the gold concentration. So plug in the chloride, plug in X for the Au concentration, and solve. So when I solve for the gold concentration, I find that the molar solubility at this point is 1.1 times 10 to the negative 5th molar. And that's an extremely weak solution. So if we want to know the percentage that remains in the solution, then I would take this new molarity, divide it by the original molarity, the 0.01%, 0.01 molar, I'm sorry, multiply it times 100 and report that as a percent. And I find about 0.11% is occurring at that point. Well, there's still one more point that's interesting in this titration, and that would be the point at which the CuCl begins to precipitate. So the third and final point occurs when the chloride ion concentration reaches its high of 1.9 times 10 to the negative 5th. So at this point, we know that the AuCl is practically gone. AgCl is really almost all the way gone as well. And the CuCl starts to fall out. So we would want to determine how much Au is left in the solution and how much Ag is left in the solution. This implies two KSP calculations, one for the gold and one for the silver. Again, we're going to know the chloride ion concentration at this point, so we're going to plug the chloride ion concentration of 1.9 times 10 to the negative 5th into both KSP calculations, solving in the first problem for the Au concentration and in the second problem for the Ag concentration. the gold concentration is dropped now to 1.1 times 10 to the negative 8th, and at the previous stopping off point it was 1 times 10 to the negative 5th. So it's now dropped to 1,000th of its initial concentration just from the last stopping off point, whereas the silver is now 9.5 times 10 to the negative 6th. And just as before, you can actually calculate the percentage of these left in the solution by taking the amount that you just calculated, dividing it by the original molarity, and multiplying times 100. And I find the percentage of the gold that's left is about 1.1 times 10 to the negative 4%. And the percentage of the silver that's left is about 0.095%. So essentially your concentration is 0, but there is still, of course, just a tiny little bit dissolved.